I'm going to present a novel attention-based pooling mechanism for material property prediction. Every technological leap in human history has been powered by material innovation. Traditionally, discovering these materials means years of lab work, which has changed to weeks of simulation by methods such as DFT. Here is where artificial intelligence is transforming material science. Deep learning model trained on existing simulation data now can predict material property much faster, such as DeepMind AlphaFold protein prediction for drug discovery. In material science, we face unique challenges when applying deep learning. The main focus of our project is how networks convert variable size structure into consistent representation while preserving the physical constraints. Graph neural network emerge as a powerful solution by representing atomic structure as graphs, where atoms become nodes and their chemical bonds form the edges, which then by incorporating the convolutional concept account for the local effect of material. Here we are summarizing our baseline network, MagNet, which has emerged as a promising framework for our task. This method is addressing the main challenge by introducing a pooling mechanism outside magnet block, which has been shown in red. MagNet, by using set-to-set pooling and iterative LSTM-based attention, preserves the structural information, but scales poorly with the system size, while simple pooling mechanisms such as min and max stays at the other end. Our goal is introducing a new pooling mechanism called AttenPool to enhance the set-to-set performance. In this work, we have been used QM9 dataset, same as magnet, consisting of around 130,000 molecules and predicting the bond gaps as the output. By replacing the pooling mechanism with a transformer block, we have defined our attention pooling architecture, in which the hierarchical attention mechanism maintains both local atomic environment, key and values here, and global structure feature, queries, which then will achieve better computational scaling. Here you can see a summary of advantages of our approach.
This is Yijun, and I will introduce the following part to you. One significance of our model is that it's very fast. So, set-to-set, the original implementation of magnet is far slower than our AttenPool on this certain task. We also compare this with some ground-based, the simplest pooling methods. They're only a little bit faster than AttenPool. And if we do a naive analysis, simple pooling goes with O and L. N is the number of nodes or edges. L is the feature dimension. While our AttenPool goes with 2nL squared. Set-to-set goes with 8nL squared. And since in set-to-set in practice, we may use multiple layers of LSTM and recurrence for multiple times. It can only be more slowly. And then more results. So our loss function matrix are MAE, the unit is EV. This is very common in machine learning for materials. I guess maybe it's always smaller than RMSE, I guess. So if we look at the result, our AttenPool is only a little bit worse than set-to-set, while far better than the normal pooling methods. Here, max pooling is an exception. We are very curious about why it performs so well. And there are more results. Batch size influences this task far more than we expected. So we're gonna delve into why that is the case. And we're also still testing. So more results will come to our report. And finally, the conclusion: we have developed a AttenPool. It achieves a good balance between time complexity and behavior. So it's significantly faster than set-to-set, while only a little bit worse than set-to-set. And we here propose some tasks for our next step. So for next step, we can further analyze the AttenPool, including the batch size, number of hazards and public data set, etc., and try upgrade our AttenPool architecture. So currently, we only try one combination of query key and value, but there can be many combinations. And third, explore the explainability of AttenPool and max pooling. That's all. Thanks for your time. Have a nice break.